So that's the main topic of today's lecture. But before that, I should make it clear one thing which I did not emphasize last time, and that was when the idea of quarks became widely accepted. And that was after, so the question is, and the answer was after discovery of Broken scaling. And the idea that the quarks are the partons, and it became very successful. In explaining electron nucleon or neutrino nucleon or anti-neutrino nucleon scattering. I think there are two S here, right? Okay? And people also introduced the idea of something called valence quark. And then the C quarks. The valence quarks are the quarks which carry the quantum number of the particular hadron. For example, for protons, there will be a 2 U quark and a 1 D quark. So this will be the valence quark. And then the other quark pairs, which are called C quarks. And then, of course, this terminology was borrowed from chemistry, from atoms. You have valence, electron, valence, and then the other things, okay? So after this, then nobody doubted that the quarks do exist, okay? But they are confined. They cannot become free particles. So that's one thing. So let's start talking about how this was discovered. To do this, I have to introduce a couple of ideas in the renormalization group. And one idea was called running coupling constant. So any physical amplitude or Green's functions, it will have dependence on the momentum Q, and then this is a renormalized amplitude, and then there's a called mu, and then the G. Okay, this is renormalized G. So let me explain to you. This is the momentum of the experiment or something. And this mu is called renormalization point or scale. Let's call it renormalization scale. And then G is the renormalized coupling constant. And basically what you have to do is to choose just mu. It doesn't have to be identical because amplitude may involve several momentum, but this mu should be the order cube. So choose this renormalization scale, renormalization point, which is very comparable to the physical momentum. And then this coupling constant will also depend on this mu. Okay? Now, if you go through the renormalization group equations, you'll find that this G satisfies the following equation. And this T is equal to log Q, log mu. Okay. Or T, Q doesn't matter. Let's call Q. Mu, okay. So let's choose, assume this is a curve G and then the beta is like this. And let's say the beta function is this form, whatever you choose, okay? So let's call this called G1 and this called G2. Now imagine that you start with the value here, this is called G0. So suppose T equal to 0. T equal to 0 means mu is equal to some scale you are looking at, and the starting point. Then G equal to G0. Okay? Then as T increases, or the mu increases, the beta in this region is negative. If it's negative, then G of mu will decrease because dg dt is negative. So as T increases, the coupling constant is going this way. And when this coupling constant reaches this point, the beta vanishes, and then dg dt equals to 0, and it doesn't move, so stay there. Okay? Now suppose you start from somewhere here. Then on this side, the beta function is positive. So dg dt is positive, and so g will increase with increasing t. So as g increases, t increases, g will increase. So increase will go in this way, like g is this way, going that way. So let's call this G1 here. On either side of G1, if you increase the momentum, the coupling constant always converges to this G1. So this G1 is called stable friction. Now I will leave it an exercise for you to look at this point. Suppose you start from here nearby, or nearby here. You will see that the coupling constant will run away from G2. On the other hand, if you pick G2 at this point, pick this coupling constant right at this point, and because beta function vanishes, so this is a stable point because it doesn't move the coupling constant, but it's unstable. As soon as you move away a little bit from the coupling constant, you will run away from it, okay? And I ask you to do an exercise yourself. By the way, if you have a question, please raise your hand and ask some questions, okay? So this is the idea of fixed point. Now, what happened to the asymptotic freedom? Well, if you take the beta function like this, and near the origin, the beta function go like that. Okay? Now you start with a point here, and then because beta is negative, let me write down here also. Because the beta function is negative, so dc dt is negative, and so g will decrease if you increase t. So the coupling constant will be driven in this way. And then eventually when t goes to infinity, it will reach this point. And this is the asymptotic freedom because the coupling constant approaches zero. Okay? So as t goes to infinity, g will go to g star, and that's equal to zero. So this is asymptotic freedom. Now, asymptotic freedom, why is so attractive? Because if the coupling constant eventually reaches zero, then in the neighborhood of this point, you can use perturbation to compute many things. And so you can apply perturbation to it. On the other hand, in this this is called non-trivial fixed point. Because it's not near zero, and it could be 5, 10, or I don't know. But anyway, it's because g is finite and not equal to zero. So you cannot, in the neighborhood of this fixed point, you cannot apply perturbation theory to it. And for example, if you start from here, even the initial value of the coupling constant is very small, near the origin here. G is very small. But because of the beta function looks like this, it's driven to this point. So essentially the physical coupling constant, which is appropriate for this particular experiment, is not predetermined. You cannot say, I will pick a small value of coupling constant and then do perturbation to it and compute things, because you cannot. Because once you increase the momentum, the theory tells you that the appropriate coupling constant is here, not here. And the distance between here and there is finite, and so you cannot use perturbation theory. That's why even though the renormalization group was known in 1954, nobody made a big progress in making application of it. And the reason was that in QED, people believe that this is the case. And so the stable fixed point is away from zero, and nobody knows how to use perturbation theory to do any calculation. And perturbation theory was the only way people know how to do it. Okay, so that's the one thing about the running coupling constant. The other idea is called anomalous dimension. And so let's take any Green's function and renormalize. and then momentum Q, mu, and G. Okay. Now, by dimensional analysis, you know that this will be roughly something like this, mu to the power d, and then once you take out this power d, then everything will depend on the ratio. Okay? So this d is called canonical dimension. Or naive dimension. Anyway, you look at the wave function, there's some, you just count the number of powers of momentum, and you'll tell you that this is a dimension 4, 5, 10 of the mass, and then you take this out, and then everything else will depend on the ratio, right? However, let's take, should I call this? Yeah, let me call this. So once I take this dimension here, then this will be dimensionless, because this already takes care of the dimension of this G R. So this is dimensionless. Now in the renormalization group analysis, Q over mu and G mu. Then what did I say? Yeah, suppose you say put a lambda here, and let's say lambda go to infinity. So let the momentum go to infinity, and what happened to this? Even though it's dimensionless, it will correspond to a power of gamma G star. And then G is bar here, will be equal to Q over mu, and then the G star here. So, in other words, somehow the renormalization group produces extra powers and this is very similar to critical phenomena. When you're near the critical temperature, certain quantity will not depend on the canonical power behavior, but with some called critical exponents, and that's exactly what we have here. Okay? Where did they come from? We know that if you compute this quantity in renormalization, in the perturbation theory, there will be logarithms. There will be a logarithms, say a Q over mu or something, and there's some powers. And then they somehow reorganize into a power, say lambda here, say into some powers, gamma G star. So these logarithms will reorganize themselves into some power behavior. And this power depends on the fixed point I mentioned before. And this is when G star is not equal to 0. Then there is the non-trivial fixed point. Okay? Okay. So we need these two things to study the discovery of symptotic freedom. Okay. Okay. So let's go back to this tensor we started before, and that's equal to 4 pi squared. The coefficient is not important. And then we have d for x, d(I) q dot x, and then now the momentum, and then the j mu x, j mu 0, and p. This tensor appears in the construction of cross-section for deep inelastic electron scattering and so on. What I want to do now is to show you that this product can be turned into a commutator. You can do this. Okay, and then this will do why. And the reason for turning into commutator, I will also explain why I do this. You see that if I turn this into a commutator, I add an extra term like this. J mu of 0, J mu of x, right? In here, it doesn't have this term, but I add a commutator, so there's a minus sign here, but the minus sign is not important. So look at this. Now, then I have to do the integral d for x, e to I q to x, like this. Now, we know the Heisenberg equation of motion. Equation of motion, and that's when you write the operator if you have a local operator point x, you can write as e to I p, this is the operator on x, for momentum operator, total momentum x, and then all of 0, p minus I on x, okay? In fact, that we used the relations before to get this form, but since I did not do the detailed derivation, I did not show you. Now I will show it to you like this, okay? So, this integral becomes d for x e to I q dot x, and then I insert a complete set of states here, okay? So I have p j mu of 0 n, and then a sum over n, and then n j mu of x p, like that, right? And then I apply this equation here. Then this operator acting on this state will just reproduce for me the eigenvalue of this. So this becomes e to I p n dot x, and then I have a j mu of 0, and this one is next to this eigenstate, so this becomes the eigenvalue e to a minus I p dot x. Is that okay? So now these are all numbers. So this integral just becomes e for x e to I q dot x, and then I get 2 extra factors here. Yeah, there's a minus sign here. So I have e to I Pn dot x, and e minus p dot x, and then I have p j nu of 0 and j mu of 0 p. Okay. Now we can do this in. So just become 2 pi to the 4th and delta q plus pn minus 1. Okay. Now, if we draw Feynman diagram to show what does this mean, I have an electron going this way, and then I have a momentum q of the virtual photon, and then I have a p here, and then this gives me the state n. And that tells me that q plus p equal to pn. Right? But this tells me is q minus q plus tn equal to p. And if you go to the rest frame, for example, p, then the time component is q naught plus e of the intermediate state will equal to the mass of the nucleon, because in the rest frame, the mass. So you can see that this q naught equal to n minus n. And that cannot be satisfied because we know the momentum, this energy loss, energy transfer here will increase the energy of this state. So Pn is bigger than n. Okay? Because we know this. So this delta function q plus p n minus p is 0 because the argument cannot be satisfied. So I'm free to turn this product into a commutator. Why do I want to turn into a commutator? Well, because we know the commutator j nu of 0 is equal to 0 if x squared is less than 0. This is outside the icon. So this commutator cannot is not 0 only if x squared is bigger than 0 in the time region, okay? And that will give us some information. Okay, what I wanted to show is that this W mu nu, because there's some coefficient over here, E4x, and then P j mu of x, j mu of 0, P. I want to show that this integral here is dominated by icon. In other words, when you do the x integration, the x squared is very close to 0, okay? And bigger than 0. So let me show you how it's the argument is a heuristic, so you just have to swallow it. Once you get used to it, you accept it. So let's in the rest frame. momentum P. Then this Q mu, will be equal to Q0, and let's choose that there are no transverse momentum, and here there are only Q3. Okay. Now we know that Q squared is Q0 squared, and there are no transverse momentum, so this only becomes Q3 squared. Okay? Okay. Now, we can write this equation in the following form. That Q3 squared equal to Q naught squared minus Q squared. And in the rest frame, that the Q naught, I showed it to you last time, I think, is equal to mu squared, and the minus Q squared itself is negative, so minus Q squared is positive. Okay? So we can get Q3 equal to square root of Q mu squared plus Q squared. And then we, you know that in the Buchanan limit, that Q squared over 2 and mu is finite. It's finite. So mu squared over Q squared is equal to what? Is equal to you can put 2 and mu here times square, and then I have a 4m squared here to take care of the 2m squared, and then I will, let's say Q square, and then I have to give it back to Q squared. Okay, so this Q squared cancels this Q squared, give me this one. 4m squared cancel the m squared, get the mu squared. So this equal to 1 over 4m squared, and then I have a 2 and mu over Q squared, and then a Q squared. So what I'm trying to say is that this number is finite. So mu squared over Q squared is order Q squared is much bigger than 1. So we can do the Taylor series expansion. So this will give me mu plus Q squared over 2mu. Okay. Yeah, approximately. Plus higher order terms as well. All right? Now, what did I do? Oh, yeah, so. No. What I want is this W1 mu equal to some constant E4x EI Q dot x. And then like that, right? Now, what's Qx? Well, Qx equal to Q0, x0, and the Q transverse is 0 by choice. And so this becomes Q3 x3. Now you can write this as 1/2 Q0 plus Q3, and then x0 minus x3, plus 1/2 Q0 minus Q3, and then x0 plus x3. Now I'm going to use very sloppy ideas, or stationary phase. this argument is heuristic, I keep saying. But you can actually show it if you want to be more rigorous, okay? So, what it means is that Q0 plus Q3 times X0 minus X3 will be order 1. And then Q0 minus Q3, X0 plus X3, order 1. The reason is that if this product gets too big, then the exponential factor becomes oscillating. And the integration will cancel out. Sometimes positive, sometimes negative, so they tend to cancel. So it's only when these conditions are satisfied, then this integral will give you some measure contributions, okay? Okay, so what is Q0 plus Q3? Well, Q0 plus Q3, from what we have there, is order 2 nu, right? Your Q3 equal nu plus some small correction. How about Q0 minus Q3? Then the nu will cancel that one, okay? So this is equal to this, but Q naught equal to nu. So the nu can cancel, so this becomes minus Q squared over 2nu. Okay? So let's just put in here. So this equal to nu x0 minus x3, and then minus Q squared over 2 nu x0 plus x3. Okay? Okay. So, what's the x squared? Well, x squared equal to x0 plus x3 is 1/2, and then x0 minus x3, right? Oh, no, there's no 1/2, just equal. And then minus x transpose square. Now, if I forget about this, then you see that, oh no, this will be bigger than this, right? x0 plus x3, x0 minus. Because I'm dropping a negative term, so this will be bigger than that. Then this is equal to here. This means x0 minus x3, so order of Q0 plus Q3, and here means x0 plus x3 is order of Q0 minus Q3. I might have to give an absolute value or something. Then this this equal to Q0 minus Q3. What did I get? Q0 minus Q3. Didn't I write something up? Oh, here. I was looking for it. Okay. So, x0 plus x3 is equal to this, and q0 minus q3 is equal to that. So this will be equal to the inverse of that, so equal to 2 nu over q squared, right? And then x0 minus x3, x0 minus x3 equal to this, and that's 2 nu. Is that right? You guys say something? Yeah. Okay. So let's put the m here, put the m there, put the m here, put the m here, and then put the q squared upstairs, and then put the q squared downstairs. Now, this is order 1, because that's the Buchan scaling variable, and that's also order 1. So what I have is m cancel, and that's equal to q squared. I don't know, did you follow my algebra? Okay, good. So this means that the q x squared is less than 1 over q squared, and then as I explained to you, the commutator doesn't vanish only in the light cone, so this is bigger than 0. So x squared is very close to a light cone, right? So the idea is that the final conclusion is that this product, oh here, we need the commutator near the light cone. Okay? So step by step, we have been led to the idea that we need this commutator near the light cone. Now, the operator product extension. So this is a inverse operator product. Now he started with the short distance. Expansion. So we have the operator product expansion of this, say x over 2, b minus x over 2. So x is, now this is, each component is very small. I don't know, some near 0. And he proposed the following form that you have some coefficient C of n of x, and then some operator n near 0. Like that. It looks like a very innocent, but it has a very big consequences, okay? And his idea was that this is generalization of an equal time commutator. You see that the equal time commutator will be like this, x 0, and then you have a b to something, I don't know, c x or something, x minus y, and then delta function. Like that. Okay, so this is but this is not arranging there because pick up the time direction specifically. So he doesn't like this, so he generalizes to this form, and to show this expansion like this. Now, but we know that this is not a short distance. We need x squared very close to 0, but not each component very close to 0. So you need to generalize this to Lycon expansion. So many people, I don't remember who, once they realize that the deep inelastic electron scattering, the operator product you need is near Lycon, then you just generalize to Lycon operator product expansion. And this is much more complicated. So I only will write down once, and I'm going to skip it all the way. Okay. So what you have is that you have two operators. Say one half y, and then have a j nu minus 1/2 y. And then you can write them down. You have a lot of indices, okay? G nu, and then you have a c. These are some conventional notation, so you don't have to pay attention. 1, I'll tell you why this is 1. And then a y squared, and then I have O I mu 1 to mu n, and then near 0, and y mu 1, y mu 2, y mu n. Now because y, because this is a Lycon, y squared equal to 0. So each component is not 0, so individual component could be very big, and so you cannot drop this, because this can be big. Still, you have this, okay? Then there's another one, a sum over n I, and then you have sum over n I, and then Cn plus 2, and then here's 2. This corresponds to this kind of operator, this corresponds to the other one, and I y squared, and then O mu nu, and then a mu 1 mu n, and then you have I just like this I, and 0, and then y mu 1, and then y mu n, row to row. Okay? So this operator is just like this, except that all the indices are taken care of by this contracting with this y. Here there are free indices mu and nu, and associated with this mu and nu. And this one, the indices mu and nu are expressed in this g mu nu. Okay? Okay. So this is too complicated. And clearly I don't have time to go through the details. But if you are interested, you can read Chen and Li, 郑大培跟李云峰的书. They have a very detailed discussion of how we do this. Okay, so I'm going to just write this, that dx 0 to 1 f2 x and q squared. You remember this is some structural functions, x to n minus 2 like this. And then there's be correspond to some coefficient, Cn, okay, some constant, and then 1 over q squared, and then this enormous dimension gamma n at the fixed one, okay? And this assumes that the G star is not zero. This Cn is just some coefficient from this thing here. Oh, I'm sorry. The Cn will be just equal to this. It's not that simple because you have to have other indices to take care of. But basically, it's the matrix element of this operator in this state and taking care of some momentum. I don't know one more. Okay. The point is the Cn contains all long distance physics. And gamma and G star contains all short distance. So the beauty of this Lycon expansion is to separate the long distance physics and the short distance physics into this form. And the Cn contains all the long distance physics, and this is non-perturbative. Oh, actually, I should say that I would go do that when I come to the symptomatic figure. Anyway, the Cn, if you just want to, if we want to know if the theory has Yokan scaling, all we need to know is a gamma n G star. So just focus your attention on particular object to investigate whether the theory has Yokan scaling or not. And that's the enormous dimension, okay? And as you can see here, if Yokan scaling holds, then all the enormous dimension must vanish. Okay? And that's a very important conclusion. So, step by step, we are led to this idea that you have to study the enormous dimension in the given theory, whether they vanish or not, okay? Okay, I have still a few minutes before the short break. So let me tell you a couple of stories about Beckett Wilson, because he is a very special physicist. Well, first of all, he worked very hard. He's very smart. But you don't have to argue. But also work very hard. So, and he taught us that he only worked on only work on problems which were not published, solved. At least for 20 years. So whatever he worked on, he will never have any competition because everybody failed before he picked it up. Okay? Now, so all the problems you work on are very hard. As a consequence, he published very little. And a popular story going around at Cornell is the following. When he was up for tenure review, he had only published one paper. And the paper was something about multi-preflow model. You probably never heard of it because that was in the 1950s or 60s, so high energy correlation and so on. So, and of course the review committee decided to promote him, of course. But a member of the committee remarked that why did he have to publish this paper? If he didn't publish this paper, we'll promote him, and it will set the precedent that we promote someone without any publication. That would be even better, right? Now, but if you read, on the other hand, his name appears in many footnotes or acknowledgement, because many important people, Kelman and those people, always talk to him, and they always thank him for particular discussion or his suggestion or something. So his name appears in many other people's papers footnote or acknowledgement, but he did not publish very many people. Okay? The other thing is that when he got the Nobel Prize, he and his girlfriend lived together, but not married. But you probably know there's custom or tradition in Nobel Prize ceremony. The physics winner's wife had the honor to dance with the king. And Ken Wilson did not want to embarrass his girlfriend. He wanted to give him a real official title of wife. So they got married just before they went to Stockholm. So he is a very decent person. In fact, later he left Cornell because of his wife. So let's have 5 minutes. I want to talk to you another story. Is it? In 1969, I was a postdoc at SLAC, and Feynman came to visit SLAC quite often. And when Feynman visited SLAC, he and Ken Wilson have a long discussion. And Feynman was very impressed. So where did this guy come from? So he said, one day he said, who are you? Where did you come from? And it turns out Ken Wilson was Gilman's student. And Feynman was in the thesis defense exam, but he just couldn't remember. Anyway, Feynman was so impressed that from then on I'm sure he remembered Ken Wilson from this encounter. Okay, so let's have a 5 minutes break, and then we'll continue. So let's continue. Did I erase something? Okay, let's repeat what I did here. So this assumes that G star is nothing. So if Built-in scaling holds, then as q squared go to infinity, this will just become f2 of x. And therefore, this integral should be constant, independent of q squared. Right? Okay. That implies that this means all the dimensional, enormous dimension G star also vanish for all n. Now, when you have these results, some smart person, in particular Parisian, and maybe others, show that if this is the case, if gamma n G star vanishes for all n, then the theory is a free theory. Another very smart physicist, semiconductor. His observation is the following. If gamma n G star is equal to 0 for all n, then gamma n G star gamma G for general G must be small for small G. Okay? And so what you have to do is just to do one loop calculation. Just do a one loop calculation. Calculation to compute this gamma n of G. Okay? And in particular, in fact, you don't even have to do this calculation. All you have to do is to compute the beta function for small g. I think I erased it because I show you that this is g and this is a function, beta function. If the beta function near the origin look like this, then as momentum goes to infinity, the coupling constant will driven to this origin. So all you have to do is to do a calculation here for the beta function, and then to see if the sign is negative, because this is crucial, that's a negative sign. Okay. Now, after he made this observation, at least two groups of people took his suggestion and do analysis of the beta function for renormalizable field theory to see which theory will give a negative beta function near the origin. One of them is our friend, Tony Z. 你想徐一红 He came back to Taiwan quite often now. By the way, Tony Z has three brothers. One is called AZ, is called BZ, the other is called C. So ABC. This is Anthony, Benjamin, and Charles. So interesting, right? And then the other group is including David Gross and Singh, a comma. So they study almost all renormalizable quantum physics. I mean, for example, you can have phi 4, Yukawa, many others, Victor Coulomb. And then they all conclude none of this theory, none of this, get negative beta. But they also, near the end of the paper, always say that they not study the young mules, non-engaged. So they did not know whether this theory is a negative beta or not. And this is already in 1973. And then when you read it, you go back and study this history. It's a very interesting story because you know that in 1971, two already showed that Weinberg, Garshau, Salam's SU2 cos U1 model is renormalizable and how you quantize them, how to do everything. But for some reason, none of these people, anybody else, follow up to study the one loop renormalization of the young mules field. Why is that so? I don't know. But that's the fact, okay? I suspect that because they study all of this, they show that there's no negative beta function, and this young mules, how could this be very different? And also, I suspect that at the time, the theory is not familiar to everybody, and the calculation is not very trivial, and so people just didn't do it. That's my only speculation. Whether that's true or not, I don't know. But of course, you know that even though Coleman did this study, and because he made the observation that beta function near the origin is very important, so he gave the power to his student. So Coleman in the young males to his student. Every part. Now you probably know when the advisor gives a problem to a graduate student, there are only two situations. Either the problem is very hard, he cannot solve himself, or it's so trivial he didn't want to do it, or it's not important. And I don't know which way Coleman thought, but anyway, he gave the problem. Of course, then the rest is history, right? He got a Nobel Prize in 2004. And then Terry Gross and Frank Richard. This find that the beta of G is negative in the young males. So this is the case in history that the minus sign earns you a Nobel Prize. Isn't that something? Now, the quantization of this young males theory is a long history. It's a very difficult one. Oh, before I do that, let me give you the answer. When you have this negative beta function near the origin, then what happened to the Buchanan's scale? Well, it's f2 x q squared x to something like this. It doesn't become actually constant, but is log q squared over mu squared, and then there's some minus down n, and then some coefficient, okay? So there's some logarithmic scaling violation. So Buchanan's scaling is not perfect, but there's some logarithm which violates the scaling. And this logarithmic scaling violation was also confirmed experimentally. And this is very interesting because first, the data wasn't very good, very precise, so they found that the Buchanan scaling works, and then started Pareto model and everything. Now, when people found that they should have very mild scaling violation, and then the experimenters would do a better job, and they also found there's a scaling violation exists, okay? Good. Now, I was going to talk a little bit about the quantization of Yang-Mills field. The first one, well, you know, this theory was proposed in 1954 by Yang and Mills. Then, of course, they tried to quantize it, and they did not succeed. And then the person whose series they tried was Feynman. Now, Feynman originally wanted to quantize gravitation, the Einstein's general theory of relativity. But Gell-Mann was his colleague at Caltech, said, well, you shouldn't try such a hard case, you know, as a first example. You should try Yang-Mills, because Yang-Mills is very close. It's also a nonlinear theory, and it's very similar to gravitation. So Feynman tried first, but he only succeeded to one loop. And he succeeded by magic. I mean, Feynman is a magician. He somehow, something was not quite right. So he guessed it should be fixed this way and that way. And so he succeeded to one loop. Essentially found a ghost loop to one, ghost field to one loop. But he could not go on because the two loops is too complicated. And then there's some American physicists like Dewey in 1964 and so on. But the Dewey's papers are very hard to read. So even though he probably did it correctly, nobody paid attention because it's hard to understand his papers. And then Fatev and Popov in 1967 published a very short paper in Physics Letters. And it happened when Schwinger was visiting Stony Brook for one semester. So sometimes, occasionally, I would go down there to see him. And during one day, when the paper just came out, so Xi and Yang asked me, have you seen this paper by Fatev Popov on quantization of Yang-Mills? I said, yeah, I did. He said, did you understand? I said, no, I don't understand it. And he said, neither do I. So he doesn't understand either. But this story, this paper is it's an interesting story. Landau, the great physicist in Russia, did a lot of the detailed study of high energy behavior of QED. And he concluded that QED doesn't make any sense at high energies because there are lots of funny behaviors and so on. Okay, so this can only happen in Russia. He banned papers on quantum field theory in leading journals. So even though Fatev and Popov wrote a paper, they cannot publish in Russia. And then they send it out to Physics Letters, only a very short paper, okay? Now the longer paper, it's only about this Weinberg-Salam Glashow model QCD and those things. In 1972, Veltman and Benny thought that this paper, long paper, should be available to a wider audience. So they suggested, they urged the long paper by Fadev and Popov be translated into English. And the paper was very clear and very easy to understand, using Feynman's pattern. And it came out as a formula paper. And in fact, I learned the quantization of Yang-Mills field from this English translation. I'm sure many people do that too. Okay? Now, about the discovery of asymptotic freedom, there's a story about the tool. In 1971. Tool, in fact, showed in 1971 the beta function in Yang-Mills theory is negative for one loop. But he did not publish. And actually he did not think about it at all. And the reason people knew about his work was in 1971, there was I don't know how to pronounce, Marseille, how do you spell it, I don't know, in France. Anyway, and truth and the semantic. After getting off the plane in Marseille, they discovered they met each other. So on their way to the conference, to the hotels, they talk about physics. And the semantic, of course, is a kind of semantic equation. You knew all about this problem with not finding any gauge theory, not finding any quantum field theory with negative beta. So he wanted to study, instead of lambda 5 4, he put a minus sign. And of course, the minus sign is a disaster because if you compute this phi, and that's the potential. If lambda 5 4 is like this, so this is lambda 5 4. If you put the minus lambda 5 4 like this, then the potential goes like this. So there's no bottom. So the theory doesn't make sense. But he was so desperate to find any field theory with this property. So he mentioned to Earth what he was trying to do. Arthur said, oh, there is a theory with a negative beta near origin, and that's the Yang-Mills field. And Semantic said, really? What didn't you publish? And the truth answer was that, well, two things. One is that he said the way he computed beta function is not the standard renormalization procedure everybody used. It's his own method. So he was worried that when he read it up, not people will understand it. The other was that he was interested, he was totally focused on weak induction, try to find renormalization of the weak induction and so on. So he did not pay attention to strong induction. So he was not aware that in strong induction, there is such an important problem. But at the conference meeting, when the semantic gave a talk, at the end of the talk, he said, by the way, Tuhoff did the calculation and showed the beta function is negative and so on. He asked the organizer of the conference to give Tuhoff 5 minutes to tell people about his results. And that's how people knew about it. And because of this, the Nobel Prize committee did not know what to do with it. Because, as you know, that every Nobel Prize can only have a maximum of 3 winners. Now, if Tuhoff is another one, then there are 4 people, so they did not know which one to exclude. So they keep waiting and waiting and waiting. And then, of course, in 1999, Tuhoff and Veltman got a Nobel Prize for their work on renormalization of the weak inductions. And so, in 2004, the 3 people got a Nobel Prize. Now, I want you to pay attention. At that time, Tuhoff is a graduate student. So was Frank Richard. He was a graduate student. And as I mentioned to you, David Polizzi was a common student. So you see that all these 3 people are graduate students. So graduate students have a huge potential to become very successful, so don't get discouraged. Okay? Maybe, what do you have? Yeah. You recall that the original motivation for Young and Mills was to find a new field theory to incorporate isospin. Okay? Now there are 2 problems with this isospin. First is that the isospin symmetry is only approximate. Isospin. And secondly, all the known at the time have a mass. And then you know that the non-abelian gauge field, in order for it to work, you cannot have a mass. So, because of this, they did not make any big progress. In fact, this question it bothers Pauli so much, because Pauli was smart. He also thought about these questions. So when Yang gave a seminar at the Institute of Advanced Study in Princeton about this Yang-Mills theory, Pauli asked the question. I keep insisting Yang should give an answer, and Yang didn't know how to give an answer. So Yang just did not know what to do. So Pauli did not want him to continue. So he sat down. And Oppenheimer was the chairman of the seminar. And he thought Pauli was too rude. So he asked Yang to continue and finish the seminar. The next day, Pauli sent Yang a note saying that what you did yesterday left me what you did yesterday made me feel so embarrassed or something. Okay? So that's that. Now, you compare this with QCD. You see that the one, it's not an isospin, but it's a carbon. It's a hidden quantum number. Because the assumption was that colors, only color singles are observable. So, and then the symmetry is put exact. And then of course we know in QCD all the gluons are masses. So you see that this is 1954, and QCD was born in 1973. So it took about 20 years for the theory to find the proper home for its application. I should remind you the same thing about renormalization group. It was also 1954. Discovered by Gell-Mann and Low. And then, of course, later by reforming by current symmetry. And become current symmetric equation. Symmetric. And it's only these two together that you get QCD. So again, it's asymptotic freedom. What I'm trying to say is that if you have a good idea, great idea, don't worry that you cannot find a good application. Eventually it will show up, and somebody smart enough will be able to use your idea to apply to important problems. Okay? So let me talk about QCD's Lagrangian. And it's very easy to write it down. Now repeating indices are sum over at the gauge field, and then we have 4. And this F mu is equal to d mu and mu A minus d mu and mu A minus G F ABC and mu B and mu C. Okay? So this is for SU3 structural constant. What's interesting about this Lagrangian is that every term has a physical origin for it. It's not a model field theory. You have some physical input which require the existence of each term. For example, we know that this term is unique to non-abelian case theory, and then you need this term in order to have asymptotic freedom. So this term is required by asymptotic freedom. Now this quarks here, size are quarks. And then I already explained to you that the deep inelastic electron scattering data and also the low energy spectroscopy both support the idea of quarks. So these quarks come from low energy and high energy experimental data. Also, white color 3, number of color is equal to 3. And that's because a baryon can only be bound state of 3 quarks. And we know that there are no other known other states, such as QQ or Q, 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 Q. So if this is a color singlet, idea of quark confinement or color confinement, you need the physical state to be color singlets, and then because the baryons have 3 quarks, you need 3 colors. You cannot have 4, you cannot have 2. So every time in this Lagrangian, there's data to support it. Furthermore, this color 3, number of color 3, there's more application. One is E plus E minus going to hadrons. Without the 3, the cross section for this will be too small by a factor of 3. The other one is a pi 0 decay to 2 gamma. Again, without the color 3, the rate will be 9 times too small. Okay, and then what else? Oh, the actual anomaly. Cancellation. In electron weak unification. You need the 3 so you can show this actual anomaly will cancel, and the cancellation is very crucial for the theory to be renormalizable. Without this, the theory will not be renormalizable. Okay? So, before QCD, people would say, let's consider model field theory for strong interaction, so and so and so. But not QCD. QCD is the theory for strong interactions. Now, let's review the steps which led to the discovery of asymptotic freedom. you remember that the Gell-Mann chronology. Then other samples, neutrino samples, derived from chronological, and then Buchanan, based on Buchanan, based on other neutrino sample, showed proposed Buchanan scaling. And then this led to the idea of particle model. And then if you identify the partons with quarks, and then as I mentioned, that there are many successes. In electron, neutrino, scattering, okay? And then the operator product expansion and then the renormalization group shows that the Buchanan scaling will require all the anomalous dimension has to vanish. Okay? And then this led to research for a quantum field theory with asymptotic freedom. And then finally, of course, the QHD was found. Now, I don't remember exactly, but I think this is in 1964. And then here in 1973. So in less than 10 years, if you look at this list, not only the theorists, but also experimentalists collaborate together and making each step possible. So it's a fantastic time period to do particle physics during these 10 years. Now, the final thing I want to talk about is all these things led to many Nobel Prizes. Of course, the first one was a Victor for GFSI with a team, something, in 1974. Then Friedman, Kendall, and Taylor for deep inelastic electron scattering in 19 90. Then close will check. Close will check plus horizon. In 2004. In the meantime, this is, I don't know how to put it, but I'll put it here. And the two. In 1994. Yeah. Especially the two, because he discovered asymptotic freedom also. So lots of
1999.
huh?
For both of them, right?
Who?
1999.
1999. This one.
Yeah.
Is this one?
Yeah.
Okay, thank you. Oh yeah, right, correct. I wrote it down 99. You remember all this data, huh? But I feel that Bill Gates, among these people, he also deserved a Nobel Prize. But he missed all these opportunities. And I have a feeling that he probably will never get it. And really too bad. Because you follow here, it's all started from here. Started from the proposal of Bill scaling, and then led to all these new exciting developments. But he missed it, and it's too bad. But in physics, sometimes you win, sometimes you lose. So let's say the following. It's probably true that all Nobel Prize winners deserve a prize. But not all deserving people got a prize. So there are still many people who deserve a Nobel Prize, but didn't get it. See, what else do I want to say? Oh, the other one, last point. I will not go into detail, just mention. And that's the artillery and the Parisi equations. You remember that these moments equal to some coefficient and then some log q squared over mu squared and then some power like that. So there are some logarithmic scaling violations. Without this, it will be Parton model. So how do you account for this in the language of Parton model? And that's how the artillery evolution came in. The idea is that the q squared is some kind of resolving power. So when you see a quark like this, if you increase the q squared a little bit, then you increase q squared a little bit. This quark will not be like this, but will be a quark plus quark and this. Because when the q squared is not big enough, this and that just become one object, just like this. But if q squared is bigger, you can resolve these things. Then there will be something like this, okay? And so essentially that the dq if you qt going to t plus dt, then the q will equal to q plus dq. And then this dq in graph, in Feynman diagram will be something like this. Okay. So he called this a splitting function. And they show that if you include these contributions, you can reproduce all these things. So just complete the story. Namely, that again, that if you want to know the details of this, check Chen and Liu. They show you how you do this. So the QCD essentially is to zeroth order is a perturbation, is a pattern model. But if you include high order corrections, there will be a QCD corrections. So the pattern model and QCD are consistent, and in fact you can include the scaling violation in the formulation of pattern model. Okay? So that's it for today. Next week, I will talk about weak induction, electroweak unification. Okay?